Hello everyone, my name is Francisco Parada, an electrical engineering student, and today I will present my professional internship at the Coordinador Eléctrico Nacional, specifically in the Competition Monitoring Unit. My main role was to analyze the impact of the aggressive entry of Battery Energy Storage System, BESS, on the sufficiency power market mechanism. As we know, a massive renewable integration without proper capacity remuneration can lead to a bigger missing money problem to the backup terminal units, putting the grid reliability at risk. Besides the complex modeling, my internship had three general phases. First, I conducted an extensive regulatory analysis regarding capacity market methodologies, like the CNN Resolution 803. Second, I produced a massive amount of historical generation data from 2023 and 2024 to create statistical box plots analyzing thermal dispatch variability. This directly supported a confidential variability study by the unit's economist. Finally, I consolidated all the knowledge I gathered from studying the market methodologies, statistical analysis, and simulating to create a technical document titled Sufficiency Power, a Challenge in Transmission, designed to explain the risk of capacity cannibalization to the other departments. The most challenging activity was developing a novel market simulation to quantify these impacts, to make it computationally manageable but highly realistic. I reduced the 38.8 gigawatt national system to a three-zone topology: north, center, and south, using a 1,000 megawatt base and a system peak of 380 megawatts. It's crucial to note that I maintain the exact percentage mix of generation technologies from the real system. The demand was distributed geographically in 31% in the north, 49% in the center, and 20% in the south, to accurately stress the grid. The transmission lines limits of 52.4 and 81.9 megawatts were calculated using the exact same scaling ratio as the generation. For the marginal prices, I performed extensive data engineering. I analyzed the real system's day of maximum demand, filtered the specific thermal units that dispatched, and manually created the database for combined cycle units that operated strictly on a diesel that day. By cross-referencing the location using the CNN databases, I calculated a weighted average variable cost per technology for each zone, ranging from 93.9 to $2,082 per megawatt hour. Despite this rigorous setup, my initial implementation using the pulp library suffered from a critical methodology error. I attempted a simplified approach, trying to model everything at once while oversimplifying key variables. Specifically, I treated hydroelectric reservoirs as a runoff river units with zero marginal cost and oversimplified the demand variability. Because I ignored the opportunity cost of water, the optimizer irrationally depleted the reservoirs at the very beginning of the simulation. Furthermore, the model failed to link solar curtailment with battery charging cycles, resulting in a stepwise unrealistic dispatch. To solve this, I implemented an incremental modeling methodology and migrated the optimization to PIPSA, Python for Power Systems Analysis. In PIPSA, I modeled hydro plants as storage units with strict annual energy limits. This was the game changer, enabling interporal arbitrage. The opportunity cost of water emerged naturally as the shadow prices of disabled thermal generation. I simulated 17,544-hour horizon for 2023 and 2024 by enforcing our scale transmission limits. Zonal price decoupling emerged natively, accurately reflecting real grid congestion and allowing BESS to charge properly during zero-cost solar curtailment hours. Ultimately, this PIPSA model successfully generated optimal dispatch profiles that empirically demonstrated the best market impacts for the unit. On a personal level, the internship was the ultimate test of my academic background. Specifically, my university courses in power systems and electrical markets were absolutely key. Without them, understanding the regulatory framework, the optimization, the logic, and the physics of the grid would have been impossible. I learned that engineering excellency requires validating critical assumptions early and discussing methodologies with experienced peers. Thank you very much for your attention.